In this video, we are going to explore and extend our thinking about similar figures. In 6.3, we talked about in similar figures, we have the ratio of sides and the ratio of perimeters is the same. So in similar figures, the ratio of the sides, whatever it is going to be like A to B, which is the same thing as our scale factor. The ratio of perimeters is the same. It's also A to B. But what we're going to explore in this video is, what about the ratio of their areas? Is that A to B? Or what about the ratio of their volumes? So this packet here is meant to sort of be notes and a guided discovery of what's going to happen here. So if we look at this first example, what is the ratio of sides of triangle ABC to DEF? Since they're similar, okay, this tells us right here that they're similar, then we know the ratio of sides will be the same for all of them. So if we just look at one side here and we compare side AB that corresponds to DE, that would be a ratio of 8 to 12, which is 2/3. So what is the perimeter? Well, if we add up all the sides, the perimeter of ABC is 24 and of DEF is 36. So what is the ratio of the perimeters of ABC to DEF? We get 24 over 36, which also reduces to 2/3. So again, that's an idea that the ratio of the sides and the perimeters are the same. But let's look at the area. So what is the area of triangle ABC? Remember, area is 1/2 the base times the height. So we take 1/2 times 6 times 8, and that gives us 24. And what about the ratio of what about the area of DEF? We have 1/2 times 9 times 12, which is equal to 54. So the ratio of the areas is 24 over 54, and that actually reduces to 4/9. So we can see the ratio of the areas is not 2/3, but there is a relationship. So what is the relationship between the ratio of the sides and the ratio of the perimeters? Well, they're the same. We know that. But what do you have to do to the ratio of the sides to get the ratio of the areas? So in other words, what do you have to do to the ratio of the sides down here to get the ratio of the areas? And it might not be clear to you right there just from looking at one example, but what happens is you take the ratio of the sides and you square it. And that equals 4/9, which is that. So we square the ratio of the sides. So when we go back up here, what is the ratio of the areas? It's not A to B, it's A squared to B squared. And so this next example right here goes through the same exact process. I'm going to let you do that on your own, and you can check back to the notes to see if you have done it correctly. But if we look at what we just discovered, is if the ratio of sides is 1:3, the ratio of the perimeters is also 1:3, but the ratio of areas is 1 squared to 3 squared, which is 1/9. So let's try to fill in the chart a different way. If we know the ratio of the perimeters, then we also know the ratio of the sides. And the ratio of the areas would be 16/9, because again, we're squaring that. So what if we're given the ratio of the areas? How do we work backwards? Well, we know that 25 over 49 is equal to A squared over B squared. So what squared would give us 25? It's pretty simple, 5. And what squared would give us 49? 7. So again, in general, if the ratio of the sides is A to B, then the ratio of the perimeters is also A to B, and the ratio of the areas is a squared to b squared. So now let's look at and explore volumes. Well, if we look at the two solids that we have here, we're going to work on volume a little bit more in chapter 12, but I know you've done volume before, and I'm giving you the formulas here. So what is the ratio of the sides for the large cube and the small cube? So the ratio of the sides for the large cube to the small would be 3 to 2. So what is the surface area of the large cube? Well, the surface area is 6 times the side squared. So we get 6 times 3 squared, which is going to give us 54. For the smaller cube, it's 6 times 2 squared, which is 24. So what is the ratio of the surface areas, or in other words, the areas? We get 54 over 24, which is the reduced ratio of 9 to 4. So you can see what we did here is to go from the ratio of the sides again to the ratio of the areas, we have to square the side ratio. But let's look at volume. What is the volume of the large cube? Well, again, volume is all three dimensions multiplied together. So the length, the width times the height. And with a cube, all the dimensions are the same. So what we would get is we would get 3 cubed, which is 3 times 3 times 3, or 27. And the volume of the smaller cube is 2 cubed, which is 8. So now when we write the ratio, we would write 27 to 8. So what do you have to do to this side ratio right here to get the volumes? And again, maybe you don't see the relationship right away, but if you take the side ratio, 3 over 2, and you cube it, because it's 3 dimensions now, you get 27 over 8. So you have to cube the ratio. Okay, so again, here's another example. You can walk through this yourself and then check back to the notes, but let's jump down to this formula, or this chart again. So if the ratio of the sides is 5 to 2, the ratio of the areas would be 5 squared to 2 squared, which is going to be 25 to 4. The ratio of the volumes then is going to be 5 cubed, which is 125, over 2 cubed, so 5 cubed over 2 cubed, which is 125 over 8. So if we know the surface area is 9 over 16, to go back to the ratio of sides, I'd have to take the square root of each, which would give me 3/4. Now I'm going to take that and cube it to get over here, which would give me 3 cubed over 4 cubed, or 27 over 64. And again, last but not least, if the ratio of sides is a to b, then the ratio of the areas is a squared over b squared, and the ratio of the volumes is a cubed over b cubed. So those ideas will help you understand the relationships in similar figures for any measurement of a side, an altitude, radius, anything like that. The ratio of the sides is a to b, and the ratio of perimeters will be the same, a to b, but the ratio of areas is a squared to b squared, and the ratio of volumes will be a cubed to b cubed. And that is the end of our work here and on with